Okay, so this is part 2 of stoichiometry video, and we're going to apply the ideas of the pancake recipe to chemistry. Okay, so at the end of the last PowerPoint, I started talking about that, and now let's move on with it. Now I'm going to apply the recipe idea to chemistry. Let's look at combustion of propane. 1 C3H8 plus 5 O2 yields 3 CO2 plus H2O. So this is the balanced equation, okay? And that's fine. But you have to understand what these numbers stand for. And it says one part protein, propane, will combine with 5 parts oxygen and yield 3 parts carbon dioxide and 4 parts water. Okay, so you can consider this like a recipe. And if it was a cooking recipe, we could write it as 1 cup propane, 5 cups oxygen, 3 cups carbon dioxide, and 4 cups of water. Okay, but in chemistry, we don't use cups, we use moles. So we'll write it as 1 mole of propane plus 5 moles of oxygen yields 3 moles of carbon dioxide and 4 moles of water. Okay, so we're going to use this as our concept in stoichiometry. So what we have to do, instead of having a cup, we have a mole, and so we have to know what this amount is. All right, let's do a problem now. So here's a recipe, and what I want to know is how many moles of water and moles of propane do I get if I do the recipe 5 times. All right, for water, every time I do it, I start out with 4, and I do that 5 times, so I'll end up with 20. Okay, for propane, every time I do the recipe, I need 1. I do that 5 times, and I'll need 5 moles. Okay, so notice what happens is that our initial number, 4, becomes 20. And in the second case, our number became 1, turned into 5. So whenever we go from recipes to moles, numbers get bigger. And the way to think about that is that a recipe, okay, for the instance for water, in the recipe, you can think of it, there are 4 moles, okay? Here's our recipe. You can sort of think of recipe as a set, and inside of are 4 moles. So we just have one recipe, and then when you let them out, okay, and we do that 5 times, we end up with 20. So numbers will always get bigger when you go from recipes to moles. That means you're going to multiply, okay? Alright, so let's do another problem. This way, going from moles to recipes. So I have 20 moles of oxygen. So you can think about it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So let's say each hash is a mole of water. Every time I do it, oxygen. Every time I do this reaction, I need 5. So what I'm going to do is divide this 20 into groups of 5. So there's 1 group, 2 groups, 3 groups, okay, and 4 groups, okay. So what you do is you divide the 20 moles into groups of 5, and you end up with 4 recipes. Okay, so in this case, whenever you go from moles to recipes, you will divide. Now, going the other way, we just showed, you multiply, because what you're doing is you're emptying out the recipes, and for the moles, you divide them up into recipes, okay? Okay. All right, now what I'm going to do, is I'm do the 2 previous problems using a recipe table, okay? So I want to do the recipe 5 times, and I want to know how many moles of propane and how many moles of water I'm going to need to do it 5 times. Okay, so every recipe I need 1, And I do that 5 times, so I'll end up with 5 moles of propane to do the reaction 5 times. Now the water, every time I do it, I need 4, and I do that 5 times, so I end up with 20 moles. All right. Okay. So to do this reaction, we do it 5 times. We'll need 5 moles of propane, and we'll make 20 moles of water. Now, what I want you to take a look at is look at the moles per recipe and the moles here. So the ratio of the propane to water is 1 to 4. And if you notice, the ratio is still the same when we figure out the moles, 5 to 20. Okay, so in the next PowerPoint, I'll talk about that and more, especially when we use another technique called dimensional analysis. Okay. So what we say is the mole ratio of propane to water is 1 to 4. So we would say C3H8, one of these is related to 4 of water. And you don't have to do that now, but I want you to keep this. This is called a mole ratio, and we'll talk about it in the next lecture. Okay, and the second problem, I said I started out with 20 moles of oxygen, and I want to know how many recipes I got. Well, every time I do a reaction, I need 5, so what I'm going to do is divide the 20 into groups of 5, and I'll get 4 recipes. Okay. Now, if you look at the two problems, when we go from recipes to moles, we multiply, and when we go to moles to recipes, we divide, and that's because we're ungrouping up here and we're grouping down here. Okay, this is finding how much each chemical we need in terms of moles. However, the problem is we really can't count out moles. There are 6.02 times 10 to the 23rd particles in a mole. To measure out 5 moles of oxygen, one would need to count 5 times 6.02 times 10 to the 23rd, which is the amount of a mole. And therefore, you have to measure out 30.1 times 10 to the 23rd oxygen molecules, and that would take forever. Okay, so there has to be a easier way to count out this huge amount without counting. Okay, however, just like with cooking, when we need lots and lots of each ingredient, the trick was not to count the cups, okay, but actually to weigh the relationship. So if I know how much each cup weigh, I could figure out how many cups I have. So what we learned is we could count by weighing, and we're going to do the same thing here. Okay, the key thing here is to think of a mole as a container. All right, so let's say I have 1 mole of hydrogen. Okay, and 1 mole of carbon. Okay, they're both going to have 6.02 times 10 to the 23rd particles in them. Okay, however, they don't weigh the same because hydrogen weighs 1 AMU and carbon weighs 12 AMUs. So I went over this in a previous lecture. So 1 mole of hydrogen is going to weigh 1 gram. Okay, 6.02 times 10 to the 23rd, which will just say 1 mole, weighs 1 gram, while 6.02 times 10 to the 23rd atoms of carbon weigh 12 grams. Okay, so even though it's the same amount of stuff, they just don't weigh the same. So it's like if you have a dozen apples and a dozen bowling balls, okay, they're still going to be a dozen, but they're going to weigh differently. Okay, so what we say is that the molar mass of hydrogen is 1 gram per mole, and the molar mass of carbon is 12 grams per mole. And we're going to use this relationship. So if I need, for instance, if I have let's say I want to have 4 moles of carbon. Okay, I simply measure out 4 times 12 grams, and I'll for 48, and that'll be the same thing as 4 moles. Okay, or the other way around, you can think about is if I have like 60 grams of carbon, how many moles is that? Well, each one is 12, so we divide the 60 up into groups of 12, and I end up with 5 moles. Okay, so I don't have to count 4 times 10, 6.02 times 10 to the 23rd. I simply weigh it. Okay, we're not going to be using 6.02 times 10 to the 23rd. Just to know that inside a mole is always the same amount, but it can weigh different. So to move on, we need to find the molar mass of each of our substances in our chemical equation. And this is fairly easy to do. I showed this previously. So you just take each atom, you figure out from the periodic table, and we'll round up. So there are 3 carbons, each weighs 12. So 3 times 12 is 36. Each hydrogen weighs 1. So 8 times 1 is 8. Then add the 2 together and you get 44 grams. So if you have 1 mole of propane, it weighs 44 grams. Or we say 44 grams per mole. For oxygen, there's 2 of them, each one weighs 16. So the molar mass of oxygen is 32 grams. 1 mole of hydrogen weighs 32 grams. Carbon dioxide, each carbon weighs 12. I have 2 oxygens, 32. Add them together, I get 44 grams. So 1 mole of carbon dioxide weighs 44 grams. Notice these are 44 grams, but they're 44 grams for different reasons. And finally, water, 2 hydrogens, 2 times 1. 1 oxygen, 1 times 16, 18 grams. So 1 mole of water is 18 grams. Okay, so this is important information from when we do use our chemical equation and determine our values. So let's do a few problems. Okay, we won't do it with the chemical equation. We'll just think about what the previous slide looked at. So if I have 15 moles of carbon dioxide, all right, so we know each one weighs 44, and I have 15 of them. So we have 44, we need 15 of them. So you're going to do 44 grams 15 times. So that's going to be 666 grams of carbon dioxide. So if you want 15 moles of carbon dioxide, you need to weigh out 660 grams of carbon dioxide. Okay, notice this is you go from 15 to 360, the number gets bigger. So when you go from moles to grams, you're ungrouping because each mole has a certain mole. You can think of a mole as a group. So each of these moles has 44 grams. And what you're doing is you're emptying out 44 grams 15 times. So you end up with 660. So you're going to multiply. You're going to end up having much more than you started. And multiply is a way to get bigger numbers. Right, so let's do the reverse. Let's say I have 360 grams of water. And I want to know how many moles that is. Well, each mole of water weighs 18 grams. And you have 360 of them. And so I could mark out 360 dots, okay? Each dot represent in 1 gram of water. And what I'm going to do is do 18 grams, 18 grams, 18 grams, and 18 grams until I've grouped them all together. Okay, and when you do that, you end up with 20 moles of water. So what I did is I divided the 360 into groups of 18 per mole. Okay, and I end up with 20 moles. Okay, so in this case, when you go from grams to moles, you'll divide. Okay, because you're getting, you're grouping, and when you go from moles to grams, you multiply. Now, hopefully, you're seeing multiply and divide, and my guess is you go, oh, when I do this, I multiply, divide. But think about it. So when you go from grams, what you're doing is you're dividing up into groups of whatever the molar mass is. So in this case, you have 360, and you're divided up into groups of 18. Okay. If you go the other way, you're emptying out. Okay, so if you have 5 moles, and each one was 18, you do empty out 18 5 times, and so you end up with 90. Okay, so I'm really, when I say these in terms of words, they mean something to me. When I just say divide and multiply, I just don't mean the math involved. I actually mean the concept of what they stand for. Okay, so let's do the previous 2 problems using a molar mass table. Again, this is not a chemical equation. You notice there's no coefficients. All it is it's molar masses. So the first problem says I have 15 moles. I want to know how many grams that is. So of a carbon dioxide. Each one weighs 44. So I do 44 15 times for 660. So that was problem number 1. Okay, in the second problem, it says if I start up 360, I divide it up into groups of 18, and I end up with 20 moles. All right. Okay, so we're going to use this molar mass table to help us with our problems. Okay, so let's combine the recipe table with the molar mass table. So what you need is a balanced equation, and then you come up to your recipe table, and you need a molar mass to come up with your molar mass table. All right, so you have this. So here's the problem. So let's say I have 880 grams of propane, and what I want to know is how many recipes is that? And then what I want to know is how many moles of carbon dioxide and how many grams of carbon dioxide. So first thing you need to do is find out how many recipes. And then once you find out more recipes, you can come over here and put numbers here and then go down. So the first thing to do is figure out how many moles 880 grams of propane is. Okay. So each propane mole weighs 44, and I'm going to divide it 880 into groups of 44, and I end up with 20 moles of propane. So bring that number up here into now the recipe table. Okay, every time I do it, I need 1 mole. I have 20 moles, so you can see that I can do the recipe 20 times. Okay. Right, so if I do the recipe 20 times, okay, how many moles of carbon dioxide? Well, each time I do the recipe is 3 times, so I get 3. Do that 20, and I will get 60 moles of carbon dioxide. Okay. All right, bring that number down here. So I have 60 moles. Okay, and so each mole weighs 44. So the amount of the grams of carbon dioxide are going to be 44, 60 times. And that's going to be 2,660, I think. Okay. All right. So that's how you do that. Okay. So the first thing you need to do is find out the recipes, and then you can figure out your grams. Okay. So here's the last problem. Okay. Suppose I have 360 grams of water. And what I want to know is how many grams of everything else. Okay. So first thing you need to do is find out how many recipes. So each mole of water is 18 grams. So you can divide this 360 up into groups of 18, and you'll end up with 20 moles of water. Okay, so you need to figure out how many recipes that is. Each recipe is 4, so you can divide the 20 up into groups of 4, so you can do the recipe 5 times. So we'll bring the 5 all the way across. Okay, all right. So let's start with the propane. Every time you do it, you need 5, so you can do 1 5 times, or 5. Then you have 5 moles of propane when you do 5 recipes. Each one is 44, so you do that 5 times. So it's 220 grams of propane. Okay, in terms of the oxygen, you do 5 times, or 25. Okay, and then you do 32 25 times, and that'll be 800 grams. Okay, then you have carbon dioxide. You do it 5 times, do 5 times is 15, and then do 15 times, 660 grams. Okay. All right. Now, so to do this reaction, you need 220 grams of propane, 800 grams of oxygen, and that will yield 660 grams of carbon dioxide and 360 grams of water. Now, one more thing I want to see out of this is, if you notice, is that the sum of the masses of the products should equal the sum of the masses of the, some of the masses of the reactants should equal the sum of the masses of the products. Okay, so 220 plus 800 equals 1020. Okay, and then 660 plus 360, okay, is 1020. Okay, check. All right. So, and whenever you're so I won't get into it now, but limiting and excess, that won't be the case. But when you're given just one of the substances, everything, the mass of the products should equal the mass of the reactants. Okay, so hopefully this helps, and I'll send out some problems relate to these.